calculating the expected returns. So now we have a universe of stocks. Excellent. Now let's put them together in a portfolio and calculate its expected return and risk. We will start off by generating n random weights for each assets in our portfolio. Okay, how do we do that? We use the random generator, but drawing from a uniform distribution, and the weights is all stored here. Okay, so these are all random uniform numbers, except that we're gonna weigh them by the sum of all the weights itself. So in order to basically make the weights add up to 100%, we take the weights which was generated here and we divide it by the total of it. So we have to rescale the weights so that they all add up to 1. Basically, that's what this is. This second line is. Add up to 1, we do this by scaling the weights vector by the sum total of all the weights. This step ensures that we will be using 100% of the portfolio's cash. To calculate the mean return of the portfolio, we have to scale each asset's return by designated weight. We can pull each element of each array and multiply them individually. But it's quicker to use NumPy's linear algebra methods. The function we want is dot. This will calculate the dot product between two arrays for us. So V is equal to 1, 2, 3, and W is equal to 4, 5, 6. Then what you have is 1 multiplied by 4, 2 by 5, 3 by 6. So this is what I mean by dot product. For a one-dimensional vector, the dot product will multiply each element pointwise and add all the products together. In this case, we have a vector of weights, W1, W2, all the way to Wn, and a vector of returns. This is mu, or mean returns, mu1, mu2, all the way to n. If we take the dot product, basically what we get is something that's really similar to this. Weight 1 multiplied by mu1, weight 2 multiplied by mu2, so just add them up. So this is the sum of it, which is mu of the portfolio itself, or the mean return of the portfolio itself. This uses the sum of all the assets returns scaled by the respective weights. This is the portfolio's overall expected returns. So in essence, this is the line, this is the explanation, this is the actual execution of it. A lot shorter than the write-up, I can assure you. So if you print the expected returns of the portfolio, which is really this one here, you get the returns of the expected returns of the portfolio is 0.5073. Now don't worry if your notebook, which you clone from the directly from the lecture series, is different from mine, because I restarted my notebook and reran it. So that's why the expected return is different. Every time you run it, it's different. The reason being we have a random number generation here and before, hence the result is different. So calculating the mean return is fairly intuitive and does not require too much explanation of linear algebra. However, calculation of the variance of the portfolio require a little bit more background, which we will dig into right now. The first thing that we need to do, though, we need to cover some basics with regards to how NumPy works. We need to be aware of not a number. That's what nan means. Okay, not your nana. It's just not a number. Most of the time, all of these calculations will work without an issue. However, when working with real data, we run the risk of having not a number values in our arrays. This is NumPy's way of saying that the data there is missing or doesn't exist. These NaN values can lead to errors in mathematical calculations, so it is important to be aware of whether your array contains NaN values and to know how to drop them. So take this, we store this into the variable v, NumPy array 1, 2, we purposely create another number here, and 4, 5. So if you print it out, this is what it looks like. Let's see what happens when we try to make the mean of this array, and notice that it gives you another number. Clearly, NaN value can have a large impact on our calculation. Fortunately, we can check for NaN values with the isNaN function. So numpy.isNaN bracket the actual variable itself, and what you get is false, false, true, false, false, and the data type is Boolean. Calling isNaN on an array will call the function on each value of the array, returning a value of true if the element is NaN, and false if the element is valid. Now, knowing whether your array contains NaN values is all good and well, but what do we do with them? Or how do we remove it? Good thing is, NumPy arrays can be indexed by Boolean values, true or false. If we use a Boolean array to index an array, we will remove all values of the array that register as false under the condition. We use the isNaN function in creating a Boolean array, assigning a true value to everything that is not nan and a false to the nans, and we use them to index the same array. So in essence, that really is saying if it's nan, we give it a true, which is here. Except that we have this notation here which inverts the Boolean. Okay, and we store these into ix, which is the index. So if we print all of these, we will get 1, 2, 4, 5. These will point us to the not nan. Okay, so if we print the numpy mean of v, except that we are indexing only those which is not nan, we will get a mean value of 3. Now there are a few shortcuts to this process in the form of numpy functions specifically built in to handle them, such as nanmean, which will actually do exactly what we did there. The nanmeans function simply calculates the mean of the array as if there's no nan values at all. There are a few more of these functions, so feel free to read more about them in documentation. These indeterminate values are more an issue with data than linear algebra itself, so it is helpful that there are ways to handle them. Okay, the conclusion here. Linear algebra is really very pervasive in finance and in general. For example, the calculation of optimal weights according to modern portfolio theory is done using linear algebra techniques. The arrays and functions NumPy allow us to handle these calculations in a very intuitive way. For a quick intro into linear algebra and how to use NumPy to do more significant matrix calculations, proceed to the next section. This is what we're going to touch on, okay, including the calculation of the variance itself.